For this problem, they're asking us to find all the solutions of cotangent x times cotangent x plus 3 equals 1. And that's different than what we've seen before, because in our previous problems they said either from 0 to 360 or from 0 to 2 pi, which means just one revolution of the circle. Because of the periodic nature of all the trig functions, including the cotangent, there are an infinite number of solutions for this equation right here. And they want us to give expressions for all of them. So we're going to start by solving this equation the same way we would as if we had that restriction for the first revolution of the circle, and then I'll explain to you how to write the solution set when you're finding all of the solutions. Now, the left side of this equation is factored for us, which would be great if we had factors equal to 0. But factors equal to 0 is special, and factors equal to 1 has no properties. So no special properties for that. So the only thing that we can do is distribute the cotangent through and then see what we're left with after that. Cotangent times cotangent is cotangent squared, and then 3 times cotangent x needs to be added. And then since this is quadratic and this is a linear term, it's quadratic in nature, so I want to subtract the 1 from both sides and have a 0 over there. Now that this is quadratic, I would try to factor it. But you notice the only way to get cotangent squared is cotangent times cotangent. And the only way to get 1 is 1 times 1. And there are no factors of 1 and cotangent that are going to subtract to give a 3x in the middle. I mean, you can't do it. So if factoring doesn't work and it's quadratic, then quadratic formula is your next best option. You could complete the square, but most people like to use quadratic formula. So I need my a and my b and my c. A is equal to 1 here, b is equal to 3, and c is equal to -1. Remember that to use quadratic formula, you have to have everything on one side and 0 on the other side. Now, if this equation had been x squared plus 3x minus 1 equal to 0, then we would be using the quadratic formula to solve for x. But our variable expression in the problem that we're given is not just x, it's cotangent x. And cotangent and x have to stay together until they're separated by an inverse operation. So that's going to be one of our last steps. Right now we just want to use the quadratic formula, and since cotangent x is our variable expression, that's what we're solving for here. So it's most helpful to write cotangent x there and not just start right in with the quadratic formula. Otherwise, you might accidentally think that the values that you get for cotangent x are your answers, and they're not. So we're going to take the opposite of b, plus or minus the square root of b squared minus 4ac, which simplifies to 13, and then that's all divided by 2 times a, which is 2. So this irrational number right here is obviously not one of our special values for cotangent, and we're going to have to use the calculator to figure out where the cotangent is equal to each of these values. The plus and the minus give us 2 separate answers here, so we need to find both of those. We'll go to the calculator for that. It doesn't tell us whether we need to be in degrees or radians here. I'm going to use degrees, so it's a little easier for you to see the difference between the values that this represents and the angles that are the solutions for x. So I have a calculator page here, and as long as I'm just finding the values for cotangent x, simplifying that irrational expression, then it doesn't matter what mode I'm in because I'm not using any angles. But when I use cotangent inverse, I will be finding an angle. So I want to make sure that my calculator is in degree mode because I said I wanted to use degrees. So let's change this from radians on the angle to degrees. Double check. And now I can go ahead and enter that fraction. and I get this positive value right here. Now I don't want to keep up with all those decimals, so I'm going to save that value to a letter so that I don't have to do so much typing later. I'm going to save that value to letter A. And then I'm going to go up and select that irrational expression again and edit it from a plus to a minus to get the other value. And notice that this value is negative. So what I have here is a positive value. Cotangent x is equal to this positive value, and cotangent x is equal to this negative value. Let's take a look back at our notes page real quick, and let's draw a picture of what we're looking for. We know that cotangent is positive in quadrant 1 and in quadrant 3. So we're going to get two answers from our positive value that we just found. And we know that cotangent is negative in quadrant 2 and in quadrant 4. So we're going to get two more answers on the single revolution of the circle for cotangent. Then we'll worry about all solutions after we find that. So back to the calculator. To actually find what the angles are, we need to use our inverse cotangent. And then remember, I stored this positive value in letter A, so that's all I have to type there, and it uses all of the decimal places. So this is an angle answer right here. We'll round that to 73.2 degrees. So back on my notes, I know that this angle measure is 73.2 degrees. That's the reference angle and the answer angle in quadrant 1. I also have a reference angle here of 73.2 degrees, which is 180 plus 73.2. So the difference between this angle and this angle is 180 degrees. So if I'm writing all the solutions, I can just add 180 degrees to get to this one, add 180 again to get to this one, 180 again to get to here, a fourth time to get back to there, and every time I go around the circle in the positive direction, I'm going to hit those two angles. I could also go in the negative direction and hit those two solutions every time. So to write that as a single expression in a solution set, I want to start with 73.2 degrees, and I want to add 180 degrees times an integer that we're going to call n. N is an integer. It can be positive, negative, it can even be 0. But it means since it's an integer, I'm not going to stop halfway, or I'm not going to start at any fractional part. I'm going to add a complete 180, or I'm going to subtract a complete 180 from the angle that I start with. So that's the expression in the solution set for where the cotangent has positive values in this equation. Now we need to get the negative values. So again, I'm going to use the cotangent inverse, and this time I'm going to use the negative value, which is b. I thought I defined that, but I forgot to save it. So let me just go back here, and then I'm going to go up and highlight that negative value. This is another way you could do it without storing the letter. And I get 163.2 degrees. That's a quadrant 2 angle. Notice that it's positive because the cotangent inverse bubble is the bubble that's on top, so you always get positive angles for that. So this one is 163.2 degrees. And in the same way, this angle down here is going to be 180 degrees away from that, either in the positive direction or in the negative direction. So I'm going to start with the 163.2 degrees, and I'm going to add 180 degrees times n. And that is my solution set that gives all of the solutions, not just the ones that on the first revolution of the circle.